Hey everyone. So today we're going to go over instantaneous velocity and what it means and how it relates to the average velocity, and some interesting points about it, and how it might be used in a problem, and just some different viewpoints on it. Um, so we know that the average velocity of an object, moving at some x, that's x1 to x2, this t2 and t1, is equal to the average velocity of an object moving in this direction. Is equal to x2 minus x1 over t2 minus t1. And if we use the delta notation, it's delta x over delta t. And we know this is the average velocity. And we know that graphically, that if you have a graph like this, and this is x2, x1, and it's like this, and t1, t2, and we know it's lined up like this. We know that this is delta t, and this is delta x. But when we go to the instantaneous velocity, it's defined this. So I'm going to write it down mathematically, and then we'll talk about it. So the velocity, the instantaneous velocity, is defined as the limit as delta t approaches 0, delta x, delta t is equal to dx dt. So what does that mean? So all of that means is that if you make the delta t very, very small, what happens, delta x is going to become very, very small, and their ratios will start to approach a value as delta t gets smaller and smaller. And when you find the instantaneous velocity, there's no delta t or a gap. It is the velocity at that point in time. There is no delta t really, because delta t becomes so small, and it's not even small anymore. It kind of disappears and becomes the value at that particular point. So if you think about it, if there's this x and t, it's kind of like saying that at this point here, there's a slope. I'll use a different color. There's a slope here, and you have a graph here that's like this, and at this point here, there's slope. Let me just do that again. Maybe it'll look a little neater. If you have something like this and a line like this, the instantaneous velocity is a tangent line to a point on this slope, on this graph. So it's a tangent line to a point on this graph. That's all it is. Graphically, you can see that as delta t and delta x start to become small, they start to collapse into this tangent line, and it's just a line that's tangent to a single point on this graph. So that's all that is. So now let's give an example of this, and maybe do a problem or two involve these concepts. So I'll just flip this over. So let's see. Let's make up a problem. So let's just say that there's an object and it follows this trajectory path. X squared plus 2x plus 3. Let's just use simple numbers. Sorry, let's rewrite this as x equals t squared plus 2t plus 3. And we want to find the average velocity, and we also want to find the instantaneous velocity at let's just pick a value at x equals 2. So, and we're going to find the average velocity from time 2 to time 4. So to find the average velocity, we first need to calculate delta x within this range. So if you plug in these numbers, if you plug in 4 here, that's 16 plus 8, 24 plus 3 is 27. Let me check that again. 16 plus 8 plus 3 is 27. And then we need to find, let me rewrite this, x2 minus x1. We know that x2 is 27 and minus x1, so we plug in the 2 here, so it's 4 plus 4, so that's 8 plus 11, plus 3 equals 11. Let me check that again. 4 plus 4 plus 3 is 11. And delta t is equal to t2 minus t1. That equals 4 minus 2. So if you do this, that's 6. 7 minus 1 is 6. 2 minus 1 is 1. 2. And you know that is 8. And let's just say T's given in seconds and x is given in meters. So this is going to be 8 meters per second squared, and that's the average velocity, right? Because we did delta x divided by delta t, and we have the average velocity for the time between 4 and 2 seconds. Okay. Now, to find the instantaneous velocity at t equals 2, we first had to take the derivative of this expression here. So dx over dt is equal to, take the derivative here, which is 2t, take the derivative here, which is plus 2, take the derivative here, it's going to be 0. So this is what dx dt is. And we know that vx, the instantaneous velocity at 2 seconds, is equal to dx dt at 2 seconds, which is equal to 2 times 2 plus 2. So we know that 2 times 2 is 4, plus 2 is 6. And we know that this is meters per second. So the average velocity, is 8 meters per second within this time frame, and the instantaneous velocity at 2 seconds is 6 meters per second. So that's an example of how we use instantaneous velocity and how we can find it given like a certain type of problem. We also calculated the average velocity, and so that's all for this video.